Hi, I'm Mirazul Haq and I'm a PhD student from University of Texas at Dallas. Today I'm going to present my work EREBA, Black Box Energy Testing of Adaptive Neural Networks. This project was co-led by me, Yashpati Adlapalli, and this project was co-advised by Professor Wu Yang and Professor Kong Liu. Like many applications, the deep neural networks or DNN model has been used on edge devices also. For majority of the models, accuracy has been used as the benchmark for evaluation. However, for edge devices, the energy consumption is also needed other than accuracy. Let's take an example. For simple machine learning models or linear classification models, the energy consumption is low, but the accuracy of the models is also very low for majority of the tasks. However, for large deep learning models with billions of parameters, the accuracy is very high. However, the energy consumption is also very high. But for edge devices, we need models with which has good accuracy but which also consumes low energy. If the energy consumption during inference is not low for edge devices, it will impact the life of the battery. To save the energy consumption, mainly two types of energy saving mechanism has been proposed for deep neural networks or DNNs. First type of mechanism is called model compression. In this technique, the number of parameters of the DNN is reduced to save energy. For each input, the energy consumption of the compressed neural networks is same. The other type of energy saving mechanism is called adaptive neural networks or ADNNs. ADNN activate or deactivate certain components of this neural network based on the complexity of the input. In this work, we mainly focus on the mechanism of ADNNs. Adaptive neural networks or ADNNs activate or deactivate certain components in the neural network based on intermediate outputs and predefined thresholds. If the intermediate output exceeds certain threshold, then the corresponding component is activated. ADNNs can be divided into two types. First is conditional skipping ADNNs, which skips certain layers or residual blocks based on intermediate outputs. While the other type is early termination ADNNs, which stop the computation early and predict the final output early. As ADNN's computation is input dependent, testing the energy consumption of the ADNNs is required. In this work, we propose two types of energy testing. One is input based and another is universal. In input based testing, we generate meaningful test input, while for universal testing, we can generate noisy input. This figure explains the input-based energy testing. In input-based testing, we apply minor perturbation to semantically meaningful inputs to test if the energy consumption of the model is drastically increased or not. While in universal testing, we test if any type of input can induce energy consumption of the model that is significantly larger than the energy consumption induced by the semantically meaningful inputs. If the energy testing of the ADNNs is not done in a proper way, it can lead into fatal consequences like autonomous car crash and drone crash. Both of the scenarios can happen if the battery is drained quickly. Before going into the details of energy testing, we will first discuss about the formulation of DNN testing. Mainly, DNN testing focuses on input-based accuracy testing. As shown in the figure or as shown in the slide, the DNN testing can be presented as an optimization problem consisting of two main components. One is perturbation and another is objective function f. Here, C is a constant provided by the tester that balances between two components, and here f varies based on the objective. For accuracy-based testing, f is represented by the relationship between input and output of a DNN. Specifically, in a white box scenario, f is dependent on the output softmax values generated by the DNN. However, for energy testing, it is difficult to find f because the relationship between input and energy consumption is not well defined for DNNs. As the energy consumption of DNN is dependent on the computations, the energy consumption of ADNNs is dependent on the activation and deactivation of the components. As discussed earlier, the activation and deactivation of components is dependent on certain intermediate outputs of DNN. Hence, we can use the same optimization function mentioned earlier to present the white box energy testing, where f is a function of intermediate outputs. From the figure, it can be seen that f is dependent on the intermediate outputs generated by specific intercomputing units. Based on the white box energy testing formulation, we have proposed ILFO for energy testing. ILFO iteratively optimizes an objective function that is dependent on intermediate outputs and corresponding thresholds. The figure in the slide shows the working mechanism of ILFO. Here, ILFO is applied on a conditional escaping model where a block is activated if the intermediate output is equal to or greater than 0.5. Here, 0.5 is the predefined threshold. Here, we can see that ILFO iteratively increases the intermediate output, which was initially 0.4 to 0.5. In this work, we focus on black box energy testing. But first, we focus on how black box accuracy-based testing is performed. For black box testing, a model is not accessible to the tester. Hence, the objective function f that is earlier defined for white box testing cannot be used here. Because of this reason, the relationship between input and output of the DNN has become unknown. Although, if a test input generated on one model is effective on other models, then the effectiveness of an input is transferable. Hence, a similar model as the target black box model can be used as surrogate model. In surrogate model based testing, first we feed inputs to target model and collect labels. Then the provided inputs and the collected labels are used to train a surrogate model. Then the tester generates test inputs on the surrogate model, and those test inputs are provided to target model for testing purpose. To understand the viability of surrogate model based approach in energy testing, we conduct a study. For that study, we use 4 popular ADNNs and we train them with CIVA10 dataset. From these 4 ADNNs, we can find 12 pairs of surrogate model and target model pair. We make our conclusion on 2 factors. One is input transferability percentage or ITP, another is energy transferability percentage or ETP. ITP measures the percentage of test input that increases the energy consumption in target model, while ETP is measured based on the average energy consumption increased in target model and surrogate model by test inputs. From the study, we conclude that for majority of the surrogate model target model pair, transferability does not exist. Hence, we need an alternate black box testing method. We formulate our problem based on the finding that ADNN's energy consumption shows stepwise behavior with respect to different number of activated components. From these figures in the slide, that particular behavior can be noticed. Now, we already have formulated that for ADNNs, the input is related to the number of activated components. As the number of activated component is related to the energy consumption in a stepwise manner, a model can be trained to learn this behavior and the model can estimate the energy consumption of ADNNs. Hence, we propose EREBA, which is based on the earlier mentioned energy estimator model. In this approach, first we feed inputs to the target ADNN model and collect the energy consumption induced in the ADNN for each input. Now, measuring energy consumption can be challenging because recorded energy consumption can be noisy. For that reason, we measure the energy consumption multiple times per input and we discard the outliers to remove noise. Based on the provided inputs and collected energy consumption, we train an energy estimator model, which is a regression model. Once the estimator model is trained, we can find the relationship between input and energy consumption of the ADNNs through FEST. Hence, the F in the optimization function is replaced by AFEST for the black box testing. For universal testing, we remove the perturbation component as noisy test inputs are allowed during the universal testing. We evaluate EREBA on 4 criteria. Effectiveness is first of them. We evaluate the effectiveness of a technique by measuring average percentage increase in energy consumption induced by the test inputs than the energy consumption induced by the normal inputs. We evaluate our technique on 3 popular ADNNs, RNet, block drop, and BranchNet, and 2 widely used datasets, CIFAR10 and CIFAR100. For baseline, we have chosen natural corruptions, perturbations, and surrogate model based approach. Here, the surrogate model is trained on block drop model. We show the evaluation results for 2 ADNNs on CIFAR10 data in the slide. We find out that on average for all ADNN models, EREBA outperforms baseline in terms of effectiveness. However, when the target model is same as surrogate model, the surrogate model based approach performs better because the surrogate model based approach works like a white box approach. The second evaluation criteria is sensitivity. Through sensitivity, we try to find out the increase in energy consumption induced in ADNNs with respect to increasing perturbation magnitude. Intuitively, if an ADNN model's energy consumption spikes up with a relatively lower average perturbation magnitude, then that model is less robust. From the figures, it can be noticed that with increasing perturbation magnitude, the energy consumption increase in block drop is limited. However, the energy consumption increase in RNet is significantly higher when we increase the perturbation. The third evaluation criteria is the quality of the test inputs. We measure the quality of the test inputs based on 2 methods. First, peak signal to noise ratio or PSNR and structural similarity index measure or SSIM. In both cases, higher values mean better quality. For SSIM, the value is bound between 0 and 1. We show the PSNR and SSIM evaluation results for CIFAR10 data in the slide. It can be seen that the quality of test inputs for block drop and BranchNet is better, while the test inputs for RNet has lower quality. The fourth evaluation criteria is the robustness of EREBA. We train the estimator model on normal inputs. And for initial seed inputs, we have used normal inputs for effectiveness evaluation also. Now, it is needed to test that if EREBA can be generalizable for corrupted seed inputs also. Hence, we apply input-based testing on naturally corrupted inputs. For CIFAR10 data, we show the average percentage increase in energy consumption for normal seed inputs and corrupted seed inputs in the slide. For corrupting the seed inputs, we choose 3 corruptions or fog, frost, and snow. For majority of the scenarios, we find out that percentage increase in energy consumption is similar for normal seed input and corrupted seed input. Hence, we can say that EREBA is robust against corrupted seed inputs. Now, we will discuss 2 methodologies that use EREBA generated test inputs to increase energy-based robustness of ADNNs. First method is filter-based input detection. This method is proposed to increase energy-based robustness against universal test input. The insight of the method is based on the fact that the semantic meaning of a noisy input and normal input is different. Therefore, if we use low energy consuming convolution based models, then the model can detect the high energy consuming noisy test inputs. In the figure, we show filter-based input detection. Here, the noise filter is a low energy consuming binary convolutional neural network classifier that is trained to detect normal and universal test inputs. The filter is executed before the execution of ADNN. If a high energy consuming noisy input is provided, first the noise filter detects the input and then discards the input. Hence, the ADNN is not executed and energy consumption is reduced. The second method is gradient-based input detection. This method is used to detect input-based test inputs. As semantic difference between input-based test inputs and normal inputs is less, input-based test inputs are more challenging to detect. Hence, filter-based detection cannot be used here and new detection mechanism is needed. For gradient-based input detection, we consider the difference between predefined threshold and first intermediate output of the ADNN as a loss function. The insight is based on the fact that the gradient of the loss function with respect to the weights would have different patterns for normal input and test input. Therefore, a simple machine learning models like SVM can detect the test inputs. In the figure, we show the gradient-based input detection. In the figure, the SVM is trained on the weight gradients gathered from the normal inputs and input-based test inputs. During inference, if input-based test input is provided, based on the calculated weight gradients, SVM can detect the test input and stops the computation early. Thus, energy consumption is saved. As mentioned earlier, both the binary classifiers are pre-trained using previously generated test inputs and normal inputs. The classifiers are tested against newly generated test inputs. From the evaluations, we find that filter-based input detection can detect 100% of the universal testing inputs. For the gradient-based input detection, the results are shown in the table. For both datasets, gradient-based input detection can detect input-based test inputs with significantly high AUC scores. In this work, we first show that surrogate model-based method cannot be used for energy testing. Because of that reason, we need to establish the relationship between input and energy consumption to formulate black box energy testing. For that purpose, we propose two different objective functions to establish the relation. And finally, we also show that these inputs can improve the robustness of the ADNN based on energy consumption. At last, we want to thank everyone for listening to our talk. We hope to interact with everyone during the conference and discuss more about the work.